In the last class, we have talked about basic structural modeling in UML, and we have covered in some detail about classes and different types of relationships among classes. Today, we will go on to talk about certain common mechanisms with reference to structural modeling, and after that, we will go on to class diagrams. We have already seen with reference to OMT how class diagrams are constructed. We will now show how class diagrams are represented in UML. Following that, we will go on to certain advanced features of UML. So UML uses some common mechanisms, and the most important kind of common mechanisms that are used throughout UML is what is called a note. So a note is represented in this way by a dog-eared rectangle, and the comments are written within this rectangle. So this is a graphical symbol for rendering constraints or comments within the UML. Besides this, this sort of comments are used to attach different information to the model. For example, requirements, observations, reports, explanations, etc. Besides this, UML uses certain extensibility mechanisms These extensibility mechanisms allow you to extend the vocabulary of UML in a controlled fashion. And the common extensibility mechanisms provided in UML are notes, tagged values, constraints, etc. Are stereotypes, tagged values, constraints, etc. So what is a stereotype? We've already seen that UML provides different structural, behavioral, grouping, and notational things. However, sometimes you will need to model the vocabulary of something which is very important to the domain. And during that time, we will have to use stereotypes. Stereotypes are actually meta values. Stereotype is actually a meta type, and each stereotype creates an equivalent of a new class. In the UML's meta model. For example, if you are modeling business processes, you may need to have stereotypes for workers, documents, policies, etc. And a stereotype is represented by this keyword stereotype. And using a stereotype, different things can be represented. When you stereotype an element, you are actually extending the language of UML by providing a new building block. And this building block has its own set of properties, semantics, and constraints. So a stereotype can have its own properties, and these properties can be in the form of a set of tagged values. Each stereotype may also have its own set of constraints. And each stereotype may provide its own icon. For example, you may introduce a new icon to represent a particular type of stereotype. A stereotype is represented like this. For example, this is the notation of the exception stereotype. So you have attached this particular icon to an exception stereotype, and the particular name of this exception stereotype is overflow. Now about tagged values. With a stereotype or with a class, you may attach a value which is known as tagged value, and that is represented like this. For example, this denotes the class server, and for this instance of the server, the tagged value of processors equal to 3. Next, we talk about constraints in the UML language. With constraints, you can add new semantics or change some existing rules. A constraint specifies conditions that must hold true for the model to be well formed. And constraints can be represented in the diagram, in the UML diagram, in several ways. For example, this is the class portfolio, this is the class bank account, and you want to specify that the association between the class portfolio and the class bank account is secure, and you represent this by this constraint. Now, a bank account may belong to a corporation or a person. But you would like to specify that a bank account will belong to either a corporation or with a person, and it cannot belong to both simultaneously. This can again be represented as a constraint. You say that this or this must hold. So this is a type of constraint using multiple elements. You can represent a constraint either informally on UML or in a formal language like the Object Constraint Language, OCL. OCL provides a formal way of providing constraints. We will not go into details of OCL, but we will look at a sample rule of OCL. Suppose I want to say that for this object has the attribute wife, and the gender of wife will be female. So I can write it like this: self dot wife dot gender equal to female, and self dot husband dot gender equal to male. So these are various ways of specifying constraints in the UML language. Now we will go into diagrams, diagrammatic way of representation of various features of UML. We have already discussed about various types of diagrams that are used in UML. Let us recapitulate the names of these diagrams. So why are diagrams useful? Diagrams are used to view building blocks. what are the building blocks? Classes, interfaces, collaborations, nodes, etc. And diagrams are used to view these things. So use diagram to visualize your system from different viewpoints, from different perspectives. We use different types of diagrams. There are two major types of diagrams. One type of diagram provides a static view of the system, another type of diagram provides a dynamic view of the system. As the static view of the system is provided by some diagrams, for example, the most important being class diagram, and also we have object diagrams, component diagram, and deployment diagram. Of these, class diagram is the most important, and we will cover this in some detail. And there are several types of diagrams that provide dynamic view of the system. And the diagrams which provide the dynamic view of the system are use case diagrams, sequence diagram, collaboration diagram, state chart diagram, and activity diagram. So now we will go into class diagrams in some detail. So what is a class diagram? A class diagram shows a set of classes, interfaces, collaborations, and their relationships. So, class diagrams are the most important and most commonly occurring diagrams found in modeling object-oriented system. And as we have said, it contains classes, interfaces, collaborations, and different relationships between them. It may also contain nodes and constraints. Note that nodes and constraints may occur in any form of diagram in UML. So this is besides these classes and other things. It may also contain packages or subsystems. And there are three applications of class diagrams. There are three cases in which we commonly use class diagrams. These are, number one, to model the vocabulary of a system. We have already discussed this while discussing OMT. But a class diagram can also be used for several other purposes. For example, to model simple collaborations, and to model a logical database system. Now, since we have already covered how to construct a class diagram, we will present an example class diagram. So this is an example of a class diagram. So there's a class called company, and there are two classes, department and office. And department and office are part of the company. Company is the whole, department is its part. And there is a one-to-many relationship between company and department. Similarly, a company may have several offices. So there is a one-to-many relationship between company and offices, and company consists of offices. So this is an aggregation relationship between company and office and company and department. There's another class called the person with some attributes. The attributes of person are name of the type name, employee ID of type integer, title of type string. And the operations defined on person are get photo, which takes a photo of type, takes P of type photo, get sound, get contact information, get personal record. So this is the class person. And there's a relationship between a department and a person. There are in fact several relationships between department and person. One is the member relationship. A person is a member of a department. So this is denoted by this association relationship. So a person may belong to one or more, zero or more departments, and the department may contain one or more persons. So the multiplicity of this relationship is star on this end, one dot dot star on this end. And the role of the person in this relationship is a member. There is also another relationship between a department and a person, which is the manager relationship. So each department has exactly one manager, and a person may be a manager of zero or more departments. So this is represented by this 1 to star relationship. And the role of the person is the manager in this relationship. Now there is also some sort of relationship between these two relations. The manager relation is a subset of the member relation. And this is denoted by this constraint. This is a subset of this relation. This is a type of constraint. Now we have already talked about the class department. Department has an attribute which is the name of the department. And there is a relationship from department to department, because a department may consist of several departments. So there is an aggregation relationship of department with itself, because there may be a hierarchy of departments. One department consists of various departments. Now we'll back to the office class. The office class has two attributes: address, which is a string, and voice, which is a number, which is the phone number. And the name of the class is office, and there is relationship between department and office. So the name of this relationship is location, and this is the direction of the relationship. A department is located in office. We have already said that there is a aggregation relationship between company and office. There's another class called headquarters, and office is a generalization of headquarters. So there is an inheritance relationship between office and headquarters. Two other classes that we consider are, number one, contact information, which has an attribute address, which is a string. And secondly, the class personnel record, which has several attributes, including tax ID and salary. And there is a dependency relationship from person to personnel record, and also a dependency relationship from person to contact info. And this thing here is an interface. This is an iSecure info. A class implements an interface. We will talk more about interfaces later, but this is the notation of an interface. And the name of this interface is an iSecure info, and this presents a view of the personal record class. So this is an example of an object diagram, and which is used to model the vocabulary of a particular system. We will now look at how we model object diagrams to model a database schema. So in fact, class diagrams are a superset of the entity relationship diagram used to model databases. Now we will talk about how to model a database schema using class diagrams. Modeling a logical database system. Modeling logical database schema. So UML is well suited to modeling logical database schema. So the common way of modeling logical database schema, as we may know, is through entity relationship diagrams or ER diagrams. And class diagrams are a superset of ER diagram. ER diagrams focus only on data. Class diagrams can model data as well as behavioral relationship. Now, we give some steps of modeling a database schema from the description of the problem. So there are several steps involved in modeling a schema. First, you need to identify those schemas in your model, those those classes in your model with whose state must transcend the lifetime of the application. So whose state stays. Stays even when the application is over. The second step is to create a class diagram that contains these classes. And since these classes transcend the lifetime of the system, these classes must be persistent classes. These are persistent classes. The third step is to expand the structural details That is, look at what should be the attributes of these classes, look at the operations defined on their classes, the relationship, the cardinalities, and the structure of these classes. Finally, fourthly, when necessary, create intermediate abstractions to simplify your design. Create intermediate abstractions so that your logical structure is simplified. And finally, use tools when possible to transform this logical description into a physical design. Let us now look at an example of modeling of a logical database schema with the help of a class diagram. So the particular domain that we will be showing is a school with the different departments, different courses, instructors, and students. So we have a school or a college, and this school is a, as you can guess, is a persistent object. And the school has several attributes, for example, name, address, phone number. And there are several operations that are defined on school. For example, add student, remove student, get all students, then add department, remove department, get all departments, etc. So this is the class school, and a school has departments. So there is an aggregation relationship between school and a class called department. And the department is also a persistent object. What are the attributes and operations on department? A department has one attribute is name, and there are several operations defined on department. For example, add instructor, remove instructor, get instructor, get all instructors, etc. Now, there are two other classes that we would like to model. One is the course and other is the instructor. First, the class course. Course is also a persistent object. And the course has several attributes. Number one, the name, and the name which is a string or name, and course ID which is a number. And then we have the class of the instructors, which is again a persistent object and which has an attribute called name. Now let us look at the relationships between these classes. First, between course and instructor, there is a relationship which is the teacher's relationship. This is the teacher's relationship between course and instructor, and the direction of teaching is in this way. And the multiplicity of the relationship, it is star in this direction and 1 ... star in this direction. Then, we have forgotten the student class. We also need to have a class called the student. Student is again a persistent class, persistent object, and the attributes of student are name and student ID. There is now a relationship between the student class and a course class, and the name of this relationship is attends. A student attends a course. The direction is in this direction. A student attends a course. There is a relationship between school and the student. A school is an aggregate of several students, so there is a aggregate relationship between a school and student. And the role of the student is a member. And the multiplicity is star on this side, 1 ... star on this side. Now, let us look at relationships of these classes with departments. A department has courses. So there's a relationship between a department and course. And this is the multiplicity of the relationship. Similarly, a department has instructors. A department actually consists of instructors. An instructor is assigned to a department. So there is a aggregate relationship between instructor and department. And the name of this relationship is assigned to. An instructor is assigned to a department. And the direction is in this way. The instructor is assigned to a department. We also look at one more relationship between instructor and department, which is the chairperson relationship. one instructor is a chairperson of each department. So the multiplicity of this relationship is 0 dot dot 1 on this end, 0 dot dot 1 is this end, and the role of the instructor is the chairperson of the department, is the chair of the department. So this is the modeling of a logical database schema corresponding to the school student course instructor database. Now, so these actually class diagrams form the basic structural modeling. We will now look at a few of the advanced structural modeling features. So far, we have been concerned with one of the most important building blocks, which is called the classes. But besides classes, there are other building blocks that can be used in the UML. And these more generalized forms of building blocks are called classifiers. Classifiers are the more generalized form of building blocks in the UML. And there are 7 types of classifiers in UML. So a classifier is actually a mechanism that describes structural and behavioral features. And the most important classifier is obviously the class, which we have dealt with in detail. The other classifiers are number 2, interface. So interface is actually a collection of operations that are used to specify a service of a class or a component. More on this later. Thirdly, we have data type. So data types have operations, but they don't define the methods on the operations. Data types include primitive built-in types like integer, as well as other types like enumeration types, etc. Fourthly, we have signal. Signal is the specification of an asynchronous stimulus communicated between instances. Fifth, we have components. What is a component? A component is a physical or replaceable part of a system. And a component provides the realization of a set of interfaces. Component provides realization of a set of interfaces. Sixth, we have a node. A node is also a physical part of a system. A node is a physical part that exists only at runtime. And a node represents a computational resource. And this resource normally have memory associated with it, and sometimes it also may be associated with a particular, it may also have some processing capability. And the seventh type of classifier that we will consider is use cases. Use case is a description of a set of a sequence of actions that a system performs and that yields something which is observable to the value, which is of value to a particular actor. Sort of sequence of actions of value to a particular actor. And eighth, we have a subsystem, which is a grouping of elements which contains a grouping of elements which contains a specification of the behavior offered by the other content elements. UML also provides a notation for specifying these different types of classifiers. We have already seen how classes are specified as a rectangle whose first compartment contains the name, then second compartment contains the attributes, third compartment consists of the operations, it may have also other compartments containing responsibilities and other things. So this is a representation of a class. An interface is denoted in various ways. One of the simplest way of denoting an interface is by a circle. So this denotes an interface. And the name of the interface is written below this. For example, the name of this interface is IUnknown, and this is how interfaces are represented. Now, how data types are represented. So data types are represented by a rectangle in which the stereotype type is written, and the name of the type is given here, and other comments or constraints are written within parentheses. For example, the constraints could be that the value of int ranges from minus 2 to the power 31 minus 1, minus 2 to 31 minus 1 to plus 2 to the power 31. So this is how a data type is represented. A signal is represented again by a box with the stereotype signal. And the box contains the name of the signal. Components are specified in this way. This is how components are specified. A node is specified in this way. A use case is specified as an oval. And a subsystem is specified as a folder. With the stereotype subsystem, now let us look at what is an abstract class. Abstract class is a class which does not provide an implementation, and an abstract class is denoted by the name of the class is written in italics. Abstract classes have no interfaces. Sorry, abstract class has no instances. So this is to be distinguished from a concrete class which can have instances or objects. And then we write the name of the class. We have already seen that an interface is represented as a circle. An interface can also be represented as a rectangle with the stereotype interface written So interfaces only have operations specified on them. There are no methods. An interface is actually a collection of operations or services that a class or a component may provide. We have talked about different forms of the basic relationships, aggregation relationships, association relationships, as well as dependency relationships. There are other advanced forms of relationships that UML supports, and we will talk about some of them. So first we talk about realization. A realization can model the connection between an interface and a class or component that realizes that interface. So there may be a realization between an interface and a class, or a use case to a collaboration which realizes the use case. And so realization is, suppose you have this use case called process loan, and you have this collaboration which realizes this use case. This is denoted in this form. So this is the realization relationship. There are different forms of dependency relationship. Which contain certain keywords, containing keywords such as bind, derive, friend, instance of, instantiate, power type, refine, use, access, import. There are different types of dependency relationships, particular types of dependency relationships that are supported by the UML. So we are not going into the details of that. We will talk about a particular type of association relationship. We have already looked at association relationships. Sometimes association relationships are qualified. For example, suppose you have this class called bank, and there's a relationship between the class bank and the class account. Now, each object of type account is associated with this class, and it can be identified by a unique identifier, and we can qualify this relationship by that identifier, and this is denoted like this. So this is the account ID, which is an integer, and these two classes are related to each other and they're qualified by the account ID. So this is an association relationship, and we have qualified this relationship. Similarly, there is another kind of relationship called composition relationship, which is a type of aggregation relationship. We have seen that an aggregation relationship is denoted by a diamond on the whole part of the relationship. A composition relationship is denoted by a solid diamond on the whole part of the relationship. For example, composition relationship holds between two classes when one class is a part of the other class, and the lifetime of the component is same as the lifetime of the whole. So these types of relationships have some special name which is called a composition relationship. For example, consider the class window and consider the class frame, which is a part of a window. It is a composition relationship between window and frame, and this is denoted by this solid diamond. And a window may consist of several frames. This is a composition relationship. A frame is a part, the window is the whole. So now for certain hints for modeling with UML. When you model relationships with UML, when you model relationships in the UML, use dependencies only when the relationship is not structural. Use generalization when you have an is a kind of relationship. And try to avoid multiple inheritance. If you see that a class inherits from two other class, multiple inheritance can often be replaced by associations. Beware of cyclical generalization relationships. Try to keep the generalization relationships balanced and use association primarily when there are structural relationships. There are some other important things in UML which are sometimes used. Number one is the package. Packages are used to organize groups of elements in UML, and a package is denoted like this. The other important thing is UML is instances. Instances are a concrete manifestation of an abstraction, and an instance is denoted as similar to a class, but they are underlined. Suppose keystrokes is an instance of the class Q. So we underline the name as well as the class to which it belongs. We may also have anonymous instances, which is just written as :frame. It's an instance of an object frame. This is a named instance. This is an anonymous instance. We use object diagrams just as we use class diagrams to model classes and the relationships between classes. We use object diagrams to model the instances. We model the instances of things that are found in class diagrams. They actually represent a snapshot view of a system. So I will end this lecture by showing an example object diagram. So we have, this is an object diagram corresponding to a company department sort of class diagram relationship. We have C is one company. C is of type company. Note that this is underlined. And then there is an association between company and a department D1. D1 is an object of type department. D2 is another object of type department. The name of the department D1 is sales. Name equal to sales. The attribute name for D2 department is R&D. There's another department, D3 is a department whose name is US Sales. And there are links between C and D1, C and D2, D1 and D3. And D3 and P is a person. And this person is a manager of the department D3. The name of the person is Erin. The employee ID is 4362 and the title of the person is CGM. So these 6 things are the different objects. Now we have another object called of type contact information, which is an anonymous object which does not have a name. The value of the address is 14 BC Road. There's another link between person and the contact information. So these 6 things are the objects. These are the name equal to sales, name equal to R&D, address equal to 14 BC Road. These are the attribute values, and these are the different links between the objects. So object diagrams are sometimes used for structural modeling. Actually, more often they're used during debugging for reverse engineering of the system. So this ends structural modeling in the UML. In the next class, we will talk about behavioral modeling.